Okay, in this video we are going to talk about self-dual graphs. So we will discuss the definition of self-dual graphs and we will see one or two examples of self-dual graphs. Okay, so let me start with the definition of self-dual graphs. So a connected plane graph G is said to be self-dual if it is isomorphic to its dual graph. Okay, so this is how we define a self-dual graph. A graph is said to be self-dual if it is isomorphic to its dual graph, okay, G star. So let me give an example of a self-dual graph. Okay, let's consider K for a complete graph on 4 vertices, and let's consider a plane drawing of K4. Then after that we will draw the dual of K4 and let's see what is going to happen. Okay, so this is a plane drawing of K4. So let's draw the dual of K4 in a different color. So it has 1, 2, 3, 4 regions. So in our self-dual graph we have 4 vertices corresponding to each region. Okay, and since we have this edge, there will be an edge between these two vertices and there will be an edge between these two since we have this edge. Okay, and this edge is shared by this region and this region, so we have this edge. Okay, and for this edge we have this edge in the dual graph, and similarly we can see that this edge is on the boundary of this region and this region, so we have this edge. Okay, so one more edge is remaining. Okay, so we have this edge and that is on the boundary of this region and this region, so we have this edge. Okay, so we can see that in our dual graph G star we have 4 vertices and 1, 2, 3, 6 edges. Okay, and moreover if you look at this particular blue graph we can see that this G star, it is isomorphic to K4, our red graph. Okay, so it can be very easily verified. So we can see that this dual graph G star, it is isomorphic to K4. Okay, and that says, and since K4 is isomorphic to its dual, K4 is a self-dual graph. Okay, so a self-dual graph is a planar graph that is isomorphic to its dual. Okay, so we can very easily see that K4 is a self-dual graph. So let's look at one more graph, wheel graph. Okay, wheel graph is a self-dual graph. Okay, so let's verify for W4. Okay, then after that we will go and prove the general statement wheel graph is a self-dual graph. So let's look at W4. So W4, it has 5 vertices and 4 among those 5 vertices they form a cycle. Okay, so they form a cycle and we have one more vertex and this vertex is connected to all other 4 vertices here. So this is our W4. Okay, so let's go and draw the dual graph for W4 in a different color. So it has 5 regions and in the dual graph we have 5 vertices. Okay, and we can see that these 2 regions share this edge, so we have this edge. Similarly we have this edge, we have this edge, we have this edge. So the dual graph we have a C4 and also we have these edges, because we can see that this edge is on the boundary of this region and this region, and similarly we have this edge, similarly we have this edge, and we have this edge. So if you look at our dual graph G star, okay, we can see very easily see that it looks something like W4. Okay, we can very easily verify that it is also isomorphic to W4. Okay, and that says this W4 is a self-dual graph. So okay, if you look here closely, we can see that we have this C4, okay, and this one vertex, the middle vertex, something similar to a middle vertex here, and that is connected to each and every other vertex. Okay, so that says this G star is isomorphic to W4, and that says W4 is a self-dual graph. Okay, so and let's go and prove the general statement. W4, not W4, Wn, the wheel graph on n vertices is self-dual. Okay, so let's prove this. So by definition, we can see that this Wn, it has n plus 1 vertices, and among this n plus 1 vertices, it forms a cycle, okay, in which n vertices form a cycle, Cn. So that's what we saw here, right? This form a C4. So in general, we will have a cycle and another vertex which is connected to every other vertex in that graph, and one vertex which is connected to all other n vertices. Okay, and that's what we saw here in W4. We have the cycle and this vertex, and that vertex is connected to those 4 vertices. Okay, and that says, okay, it has these 4 inner region and this outer region. Okay, and the outer region is bounded by this cycle, and the inner region, okay, it is bounded by these triangles and this C4. Okay, so it has n faces or n regions inside the cycle Cn. Okay, that's what we saw here. So here we have 4 regions inside this C4. So it has n regions inside the cycle Cn and one exterior face whose boundary is Cn. Okay, and that's what we saw here. And if you consider this exterior space, exterior region, the boundary is this C4. Okay, and that's what we saw in that case, and that is true for Wn also. So it has n regions inside the cycle Cn and one exterior face whose boundary is Cn. Okay, and here you can very easily see that, okay, not that here these 4 edges of C4 are the n edges, okay, are these edges of these interior faces. Okay, so not that the n edges of that cycle graph Cn are the n edges of the n interior faces. Okay, so we can see that very easily in this figure. Okay. Okay, so that says if you look at the dual graph, okay, so its dual graph G dash, okay, it will have n vertices forming a cycle, okay, and that cycle it corresponds to, okay, these edges, these internal edges, okay. So its dual graph G dash will have n vertices forming a cycle, and okay, that it corresponds to n interior faces, okay. And okay, so we have something like this. So its dual graph G dash, okay, G star will have n vertices forming a cycle, and that corresponds to those n interior faces, okay, and that is what we saw here, right? Okay, so these interior faces it form a cycle. So here we have this C for city here, and a single vertex corresponding to the exterior region, and a single vertex V, okay, let's call that vertex V corresponding to the exterior face. Okay, and we can very easily see that this vertex V of G dash will be adjacent to every vertex in that cycle, okay, since the exterior face of G is adjacent to all the interior faces, okay, and that's what we saw here. Okay, so here we can see that this exterior, we call this V, and it is connected to all the vertices corresponding to this interior regions, because we can see that they are, okay, they share these edges of the cycle, okay, with this region. Okay, so this vertex B of G star, okay, it will be adjacent to every vertex in that Cn, since the exterior region or face, okay, so okay, we can call this region or faces, both are same. Okay, similarly this, okay, since the exterior region of G is adjacent to all its interior faces. Okay, and that's what we saw in this example W4, right? You can see that this vertex V is connected to all the vertices corresponding to these regions. Okay, so this vertex V of G star will be adjacent to every vertex in the CN, since the exterior region of G is adjacent to all its interior faces. Okay, so we have this Cn, okay, and that vertex V is connected to all other vertices of this Cn. Okay, so it looks exactly similar to Wn. Okay, and that's what we saw here. If you look here, so we have this Cn. Okay, we have Cn and this vertex. So in that, this vertex will correspond to this thing here, and we can see that this vertex is connected to these vertices. Similarly, this V is connected to these vertices. Okay, and that says G star is isomorphic to Wn. Okay, we can very easily see here. So G star is isomorphic to Wn. Okay, we can very easily establish a one-to-one correspondence here, right? If you look in this example, so we can correspond this W to this vertex, okay, and these vertices to these cycle vertices. Okay, this one with this one with this with this, and this with this. Okay, so here also we can do the same kind of thing. Okay, so G star is isomorphic to Wn, and therefore Wn is self-dual. Okay, so we proved wheel graph is a self-dual graph. So here this gives Wn, it gives us an infinite family of graphs that are self-dual. Okay, so let's prove a statement related to a plane graph. Okay, so it's a very simple statement and it is very easy to prove. So if a plane graph G on n vertices and m edges is self-dual, then we have this relation. Okay, m is equal to 2n minus 2. Okay, so let's go and prove this statement. Okay, so I think we can very easily verify this in these cases. For example, if you consider this Wn, okay, Wn, it has five vertices. Okay, so if it is a self-dual graph, then the number of edges is 2n minus 2, right? So that says m, number of edges, m must be equal to 10 minus 2, which is, okay, so, okay, not 5, I think, 4, okay, it's W4, right? Okay, anyway, it has 5 vertices and, okay, 8. So here we can see that it has 1, 2, 3, 4, 5, 6, 7, okay. Vertices, and similarly you can also see the result holds for K4 also. So here K4, it has 4 vertices. Okay, so that says, okay, it is like 2 times 4 minus 2, which is equal to 6. Okay, we can very easily verify 1, 2, 3, 4, 5, 6. Okay, anyway, it is a complete graph. It has 4 vertices, so it must have 6 edges. Okay, so we saw it is true for those 2 examples, and let's go and prove the general statement. Okay, it's a straightforward thing. Okay, we use a relationship, a property of dual graphs, and we apply Euler's formula. Okay, so let G be a plane graph on n vertices and m edges, and let G star be the dual of G. Okay, assume that, so you are given that G is self-dual. So assume that G is self-dual. So if G is self-dual, then G star, okay, it is isomorphic to G by definition. Okay. So that says we have the number of edges, okay, n star, number of edges in G star, okay, it is going to be equal to n. Okay, by definition, okay, G star is isomorphic to G, so they must have the same number of vertices. Okay, so let's call this equation 1. Okay, and since G dash, okay, G star is the self, okay, is the dual of G, so that's what we assumed here. Okay, let G star is the dual of G. Again, since G star is the dual of G, the number of vertices in G star is equal to the number of regions of G. Okay, and that's how we define the vertices of the dual graph. Okay, since G star is the dual of G, the number of vertices in G star, okay, that is going to be, okay, equal to number of regions of G. Okay, so hence we have n star equal to R, okay, and by 1 we have that is equal to n. Okay, so let's call this 2. So by Euler's formula, we have n minus m plus R equal to 2, and by 2 we have R is equal to n. Okay, and that says m is equal to, okay, we can take this to the other side and this 2 to the other side, which is equal to n minus, okay, n plus R minus 2, okay, and we have R is equal to n, so n plus n minus 2 by 2, and here we have 2n minus 2. Okay, and that's what we want to prove. Okay, so that says if a plane graph G on n vertices and m edges is self-dual, then m is exactly equal to n minus 2. Okay, next, normally we ask this question, suppose that we have two graphs G1 and G2 that are isomorphic, then whether the dual of G1 and G2 are also isomorphic. So that is not going to be true in general. Okay, so that's what we are going to show next. Okay, so isomorphic graphs need not have isomorphic duals. Okay, so this is an example that demonstrates this statement. Okay, isomorphic graphs need not have isomorphic duals. Okay, so let's consider these two graphs G1 and G2 and consider the dual of G1 and G2, and let's see what is going to happen. So we will see that, okay, here very easily we can see that these two graphs are isomorphic. Okay, so we have this correspondence A to A dash, okay, B to B dash, C to D dash, and so forth. Okay, and that says these two graphs G1 and G2 are isomorphic. Okay, but we can very easily see that their duals are not isomorphic. Okay, let me give an argument of that one. Okay, so okay, looking at this particular graph, we can see that, okay, it is clear. Okay, this G1 is isomorphic to G2. Okay, we have this correspondence A to A dash, B to B dash, etc., etc. Okay, you can very easily verify that. Okay, and let G1 dash G1 star and G2 star be the duals of G1 and G2. Okay, so if you look at this particular graphs G1 and G2, okay, here we can see that in G2, okay, it has a region bounded by these 4 faces. Okay, so that says in our dual graph, the vertex corresponding to this region will have degree 4. Okay, but here if you look at this graph G1, okay, we can see that every graph is bounded by a triangle. Okay, so it won't have a degree 4 vertex in the dual. Okay, and that's it. And that says G1 star is not isomorphic to G2 star. Okay. So here you can very easily see that not that G2 has a region. Okay, so this region bounded by 4 edges. Okay, bounded by 4 edges. Okay, whereas if you look at this graph, it has no such region. Okay, so whereas G1, it has no such region. Okay, so that says if you look at the dual graph G2, it will have a vertex of degree 4, whereas if you look at the dual of G1, there won't, okay, that graph it won't have such a vertex. Okay, so the dual G2 star of G2 will have a vertex of degree 4. Okay, but such a vertex, okay, it won't be there in G1 star. Yes, but there is no vertex of degree 4 in G1 star. Okay, so hence we can very easily see that G1 star is not isomorphic to G1 star and G2 star. These two dual graphs are non-isomorphic. And thus we have this relation. Okay, so we saw G1 is isomorphic to G2, but G1 star, it is not isomorphic to G2 star. Okay, so that says isomorphic graphs need not have isomorphic dual. So this particular example, it will demonstrate that. Okay, so in the next few videos we will discuss some statements related to dual graphs.